As I've said before, our question we're interested in answering is how does the body maintain a constant pH of 7.4 in the blood? And the answer is it does so with a buffer, which is a roughly equal mixture of a weak acid and its conjugate base that can neutralize added challenges of acid or base and maintain a constant pH. We've discussed what weak acid and conjugate base are, and what I'd like to discuss now is what does it mean to neutralize added challenges of acid or base, other acids or bases that we might ingest or have as part of our body. So let's keep going. Acetic acid is a weak acid, and I already told you that it's in our body. Could we use a roughly equal mixture of acetic acid and acetate in our blood to maintain a constant pH of 7.4? Well, let me remind you of one thing that's relevant to this discussion. The pKa that governs this relationship is 4.75. And the answer to the question that I just asked is the proton tight enough or loose enough to behave as a buffer in blood? That's what pKa means. A definition is a measure of how tight a proton is bound, and lower is looser. Well, let's consider this idea of neutralization on the next page. To demonstrate the concept of neutralization, we're going to perform a theoretical titration of acetic acid. Here it is again. We have acetic acid. Let's say we had acetic acid in our blood. Could that behave as a neutralizing species for added challenges of base? Well, let's do a titration and figure that out. What a titration is to take acid, put it in water, throw a pH meter in, and measure the pH at the beginning of the experiment. Now, the acetic acid would have a pH somewhere in the low range, 2 to 3. After all, it is an acid. Now, what if we threw sodium hydroxide at it by dripping that in? We'll put sodium hydroxide down here on the x-axis of this chart, and the units here are equivalents of sodium hydroxide. That simply means how much ever acetic acid we have in the solution, we're going to put the exact same concentration or amount of sodium hydroxide in. Now I want you to consider what would happen if we threw some sodium hydroxide in water without acetic acid. Sodium hydroxide is a strong base, and the pKa would go up very rapidly if we did that. Now, you don't have to draw that in there because that's not what we're doing. That would not maintain a constant pH. But let's consider what would happen if we did it with the presence of acetic acid. Now, let's consider what the acetic acid and acetate concentrations are at the beginning. Remember, acetate is the conjugate base over here. As it turns out, like we said, acetic acid is a weak acid, and that means almost all of it, let's just say approximately 100% of it, is going to be in the acidic form, and approximately none of it, or 0%, is going to be in the base form at the beginning. However, if we then go ahead and throw sodium hydroxide in, what happens is instead of the OH raising the pH rapidly, the proton of the acetic acid and the OH of the sodium hydroxide can neutralize each other, and you end up with two new species. Do you remember what happens when you neutralize an acid and a base? You end up with water from the OH and the proton, and you also end up with a salt where the sodium counteracts the negative charge of the acetate. That's a neutralization reaction, and that helps keep the pH from going very high. In fact, we can see that the pH is going to go up just a little bit here as we add more and more sodium hydroxide because it's being neutralized by the acetic acid. Now, when we get out to about 1/10 of the way along, at this point you would have about, well, let's just make another line here. You'd have about 10% converted to acetate, and you still have 90% as acetic acid. So we've managed to keep the pH relatively unchanged, but it came as a cost. We used up some of the neutralizing acetic acid. We've lost 10% of it. Well, we can keep doing that, and we can add more sodium hydroxide. We can neutralize more of it, and eventually you get to the point where you've used up 50% of your acetic acid, and you have 50% base now. That's a really important point, and I want to put an arrow right there. It's the midpoint of the titration. I'm just going to write down this term right here for now. We'll come back to it later. This is an ideal buffer. Remember, buffers are roughly equal mixture of acid and base. In this case, a 50-50 is exactly equal mixture. That makes it really an ideal buffer. Before we come back to that, let's keep on going. What if we continue to add more sodium hydroxide? As we do so, the buffer maintains a neutralizing presence and keeps the pH relatively constant. By the time you get over to here at about 90% of an equivalence, you start to run out of acetic acid. And at that point, it gets harder and harder to neutralize things, and eventually the addition of sodium hydroxide kind of shoots the pH up because you can't neutralize things anymore. Eventually, you get to the point where it's all converted, essentially all converted to acetate, and there's very little or none left as acetic acid. At that point, you have lost the ability to keep the constant pH. Okay, that's what a titration looks like. Let's return to the very center here where we have an ideal buffer, an exactly equal mixture of weak acid and its conjugate base. Like I said, you can add sodium hydroxide for a while and you will be able to keep the constant pH. However, if we were to turn around and start adding strong acid like hydrochloric acid, we would go backwards. The protons would start consuming the acetate, or they'd be neutralized by the acetate base, and instead of having the pH drop rapidly, it would stay relatively flat. And that would occur until you ran out of acetate down here, and then things would go south pretty quickly. So, right in the middle, you can withstand challenges of base, you can withstand challenges of acid, and maintain constant pH for a good while. And that is how buffers are going to work. They do so because they have an acid, like acetic acid, that can neutralize added base, and they have a base, like acetate, that can neutralize added acid. And it's all about neutralization. So that's a good start. Let's continue with these ideas on this page on the next video.